thank you for your introduction, Mr. Chairman. In the title, it actually said new damage parameters, but I'm actually going to speak about really just one damage parameter and some all damage parameters. Well, first of all, I would like to thank my colleagues from the University of Malaga, the University of Jaén, and from Dover Corporation for their help. Before everything, I would like to say that I'm kind of new in this business of multi-axial fatigue. So when we started maybe 3 or 4 years ago, actually, working on multi-axial fatigue, we looked at the literature and we saw that there were quite a few models like stress and strain-based models, fracture mechanics, energy criteria, and then we also saw the critical plane approaches. So we thought that actually the critical plane models were quite interesting because they, well, in principle, they give information not only about the fatigue life, but also the dominant crack plane. So since we were involved a couple of times in the crack path conference, we thought, well, maybe this is like it's interesting because if we already have the initial crack orientation, then we've got like kind of half of the problem sorted out. So that's why we decided to do the first preliminary analysis on with the multi-axial, with the critical plane models. So we thought of using some of the most cited planes and they were WANG-BROWN, FATEMI-SOCIE, and Smith, Watson, and Topper. And actually, last year we happened to go to the multi-axial conference in Seville, and Fatemi proposed a variation of his model from 1988 with SOCIE, and he said that it was much better and it would improve the fatigue life. So we thought, well, I mean, since we're trying different models, why not try it? And so we gave it a try to this FATEMI, we called it new FATEMI model for predicting the fatigue life and the crack orientation. But before everything, we thought we could apply the models just like we just take them and apply them, but of course we need to do more things. So we needed we had a structural steel, and we had to do a whole characterization, both monotonic and cyclic. So that was actually the first thing that we needed to do. So we took some, the steel is a structural steel at 355, low carbon steel. We did some monotonic tests for finding tensile and compression properties. We also had to get involved with the biaxial machine. We were not really looking forward, but in the end that's we had to. And we had to use the biaxial stesometer, which is quite tricky because we see this this pin which holds the sample. It doesn't really tighten it doesn't grip very tightly. So in the end, you need to be really careful when you mount the stesometer, and on top of that, if the machine moves a bit more than normally, then it's the whole experiment is ruined because it's actually strain control. So that was one of the difficulties that we found in the experiment. Yeah.
Let me give you a small piece of sandpaper.
Small piece of
sandpaper bond in the specimen. It's going to solve the problem.
Yeah.
Just bond a small piece of sandpaper.
Yeah, just where the pin goes.
Over the sandpaper.
Okay.
It's going to solve the problem.
Great. Yeah. Okay. So yeah, so hopefully next time we can go from 4 Hertz to maybe 10 Hertz.
Don't be too optimistic.
Okay. So yeah, anyway, we managed to measure the cyclic properties, both in tension and compression and torsion, and then we did well, few in-phase and out-of-phase tests with zero mean strain and with imposed axial and shear strain. And as I said, well, we did 13 in-phase tests and 11 out-of-phase tests. Actually, in this talk, I will only speak about the results of the in-phase test, because because it's just easy. So we can see here the results of all of the tests. This figure, well, it was useful for us to see that we were not doing everything very wrong, because well, we can see that the in-phase and out-of-phase. So the out-of-phase experiment had a lower fatigue life. So that made sense, and it agreed with the literature. So we thought it was not, we were doing everything, well, more or less all right. So we started using the critical plane models, and we found that, well, as I said, that they give a prediction of the fatigue life, but also the crack orientation. So that was interesting. And yeah, we started using, well, for example, so the first one was the WANG-BROWN model, where that is based on the assumption that the cyclic shear strain caused the crack nucleation, and then the normal strain, the cyclic normal strain, contribute to the crack growth. By the way, these figures I took them all from the Socie Marquis book. So they speak about a critical plane that would be the one with the maximum amplitude of shear strain. And actually, well, reading the literature, I found that like roughly half of the literature says that this is the critical plane, the one with the, well, for example, according to the WANG-BROWN model, the one with the maximum shear strain. But then the other half of the literature, it says that the critical plane is the one with the maximum damage per meter, which is not exactly the same. Sorry?
Yeah.
So the real one is, this is what the critical plane should be. The one
No,
with,
we knew the lower one.
the one with the maximum damage per meter.
Originally it was the first one, but I guess that the second definition is better.
Okay. So we actually, we tried a bit both, but it is, I mean, it was a question that I wanted to ask around, because I keep seeing papers, and recent papers as well, where they assume that the critical plane is this one, and some of the papers that get published regularly, they use this one as the critical plane, so the plane with the maximum value of the damage per meter. WANG-BROWN also gives, of course, a relation between the damage per meter and the life. We looked also, as I said, to the FATEMI-SOCIE model. Again, it uses the same critical plane, so it assumes the shear strain caused the nucleation, but it is the normal stress that contributes to the crack growth that we see in this component. Again, we see we have a relation between the damage per meter and the fatigue life. We also use the Smith-Watson-Topper model that is used for materials with mode 1 or tensor failure mode, and it is based on it assumes that it's a cyclic normal strain that causes the failure. In this case, the critical plane and the damage per meter are coincident. Again, we have a relation between both. And finally, the new FATEMI-SOCIE model, it is similar as the other model. It is based on, so it assumes the nucleation of the crack is caused by cyclic shear strength, and the normal strength, the normal stress on the crack plane is the one that also contributes to the crack growth. But instead of like using here the yielded stress, to make this term dimensionless, it uses the angular stress range on the maximum angular shear strain plane. So that's the small difference. Last year he said at the conference that he would get much better results. So we just wanted to try. It also uses sensitivity factors that depend on the fatigue lag and the cyclic axial parameters, and torsion parameters. And well, last year he used it depends on the material, and in our case it was 1.1, the value of this scale. So we had to find do an evaluation of all the planes. For the proportional loading, it was a bit more clear to us, because the maximum value was through the cycle, it was easier to be identified. For the non-proportional, it was a bit more difficult. We had to evaluate all the points. And then we plotted the evolution of the damage parameter and the shear strain amplitude. And we saw that, well, what I was saying before, the critical plane, both according to FATEMI-SOCIE and WANG-BROWN, would be those two, the one with the maximum value of the shear strain amplitude. But then the maximum value of the damage parameter, for example, in the case of FATEMI-SOCIE, is not exactly this value, that here is like 105 or so, but it's slightly bigger value, and then this other point, the maximum value of the damage parameter is a bit shifted as well. So, the other thing is that from a mathematical point of view, the maximum range actually happens in one single point, but from a material science point of view, where we have like microstructural features, really, like any type of effects or microstructural barriers, then the point with the maximum value of strain is it doesn't make sense to use just one single point. So I mean, this is so what people normally do is, instead of considering just the one single plane, to use a range of planes. So provided so between plus minus 18 degrees, we would have the strain value would be 90% of the maximum, which makes sense. So we looked at the different plane orientations, and we observed that if we look at the first critical plane predicted by FATEMI-SOCIE, so the one with the maximum, one of the planes with the maximum shear strain amplitude, we saw that only two of them agree, using this 90% of the maximum value. If we use the second shear strain, the second critical plane angle, some 5 other values agree. Sorry, 6 values, 6 planes agree in the out of the 13 specimens that we tested, and then we looked at the maximum value of the damage parameter, and for WANG-BROWN, none of them agree. And for FATEMI-SOCIE, 5 planes agree. And for Smith, Watson, and Topper, none of them really agree. So nevertheless, well, we found that the agreement between the plane orientation and the one predicted by the model was not very good. But nevertheless, we used the model for looking at the fatigue line. And this is well, a summary of all the tests. We can see that, well, we're plotting here the estimated fatigue line by the different models and the experimental fatigue line. And we see that the FATEMI-SOCIE tends to give better estimation than WANG-BROWN and Smith, Watson, and Topper. We can also see that the new FATEMI model is in pink. It improves the predictions compared to the old FATEMI-SOCIE, but the problem is that some of the predictions are non-conservative, so I'm not sure if it's really an improvement. And then, yeah, as I said, so WANG-BROWN and Smith, Watson, and Topper were all conservative, but slightly worse than the FATEMI-SOCIE model. So that's it, really. So basically, to conclude, we've done a series of tests. So we produced a new database with experimental biaxial fatigue data for a widely used structural steel. We observed that the real failure plane and the critical plane predicted by FATEMI-SOCIE agreed a bit to a certain extent, and WANG-BROWN less, and Smith, Watson, and Topper for this series of tests that we did didn't really agree. The best predictions were produced by the FATEMI-SOCIE model, and a slight improvement was obtained with the new FATEMI-SOCIE or new FATEMI parameter. But the prediction were, some of them were non-conservative. And finally, that the WANG-BROWN and Smith, Watson, and Topper predictions were slightly worse than FATEMI-SOCIE, and they were all conservative. Finally, I would like to acknowledge the institution that funded our work, and I would like to thank you for your attention.